The universe should be loud. 200 billion stars in our galaxy alone, 2 trillion galaxies in the observable universe, 13.8 billion years of cosmic history for something, somewhere, to have gotten a head start on us. By any reasonable statistical accounting, the sky should be humming with radio chatter, laced with the faint infrared glow of alien engineering projects, dotted with probes, satellites, and signals from civilizations that got a 10 million year jump on humanity's own 200,000 year existence. Instead, there is silence. Total, unbroken, almost eerie silence. Every radio telescope humanity has ever pointed at the sky, every survey, every search, across more than 60 years of dedicated, serious scientific effort, has returned exactly the same result. Nothing. Not a single confirmed signal. Not one unambiguous artifact. Not the faintest whisper of anyone else out there, anywhere, at any point across the entire observable universe. That silence has a name in scientific circles. It's called the Fermi paradox, and for most of its history, it's been treated as a fun, speculative dinner party question, the kind of thing you bring up over drinks. But there is a specific, formal answer to that paradox, proposed by a working economist in the 1990s, that a meaningful number of serious scientists have described in their own words as something closer to a genuine warning than a fun thought experiment. It's called the Great Filter, and it doesn't just ask why we haven't found aliens. It asks something considerably more uncomfortable. Whether the reason we haven't heard from anyone else out there is because almost nothing, anywhere, ever survives long enough to be heard. By the end of this video, you'll understand exactly what the Great Filter actually proposes, why serious physicists, economists, and philosophers take it seriously rather than dismissing it as science fiction, and why the specific question at its core, whether humanity's own filter is already behind us or still somewhere ahead, might be the single most consequential open question our species has never properly sat down to answer. Let's get into it. To understand where this theory actually comes from, you have to go back to a casual conversation that happened over lunch at Los Alamos National Laboratory in the summer of 1950. The people at that table weren't casual observers. They were some of the most accomplished physicists of the 20th century, veterans of the Manhattan Project, deeply steeped in exactly the kind of statistical, big-picture thinking that made them uniquely suited to notice a genuine glaring inconsistency in how humanity thought about its place in the universe. Among them was Enrico Fermi, the Nobel Prize-winning physicist whose work had helped usher in the nuclear age itself. According to the most widely told version of the story, the conversation had drifted almost idly toward the topic of UFOs and the possibility of interstellar travel, when Fermi, after sitting with the numbers for a moment, reportedly blurted out a simple, four-word question that has haunted scientific thinking about extraterrestrial life ever since. Where is everybody? It wasn't a rhetorical throwaway line. Fermi had done, in his head, roughly the same basic calculation astronomers still do today, and the math simply didn't add up. Given the sheer number of stars in our galaxy, the substantial fraction of those stars likely to host planets, and the billions of years those planetary systems have had to develop life and, potentially, technological civilization. Even a civilization expanding at a comparatively modest pace, using nothing more exotic than slow, sublight speed spacecraft, should be capable of colonizing an entire galaxy, the size of the Milky Way, within just a few tens of millions of years. An almost negligible span of time compared to the galaxy's roughly 13 billion year age. If even one civilization anywhere, at any point across that entire span of cosmic history, had gotten a sufficient head start, the galaxy should already be full of evidence of their presence. It isn't. That gap between what the numbers say should be happening and what we actually observe is what formally became known as the Fermi paradox. And in the 75 years since that lunch conversation, an enormous body of serious scientific and philosophical work has been built specifically around trying to explain it. Most attempts to resolve the Fermi paradox fall into one of a small handful of broad categories. Maybe intelligent life really is exceedingly rare, the product of an improbable sequence of lucky planetary conditions that Earth alone happened to receive, an idea formalized by geologist Peter Ward and astronomer Donald Brownlee as the rare Earth hypothesis. Maybe advanced civilizations exist, but deliberately stay hidden, watching us the way a zoo watches its animals, careful not to interfere. An idea known simply as the zoo hypothesis. Or maybe, as we'll get to shortly, everyone out there has very good, very rational reasons to stay silent, deliberately and permanently. Much of this debate traces back to another famous piece of scientific scaffolding, the Drake equation, formulated by astronomer Frank Drake in 1961 as a way to organize the many separate factors that would need to multiply together to estimate the number of detectable civilizations currently active in our galaxy. The equation multiplies together variables like the rate of star formation, the fraction of stars with planets, the fraction of those planets capable of supporting life, the fraction of those that actually develop life, the fraction of that life that develops intelligence, the fraction of intelligent life that develops detectable technology, and finally, the average length of time. Such a civilization remains detectable before it either destroys itself, evolves beyond detectability, or simply falls silent. Depending on which values you plug into each of those variables, and reasonable, good faith scientists disagree enormously on nearly every single one of them, the equation can be made to output anything from we should be functionally alone in the galaxy to the galaxy should be teeming with thousands of active civilizations. The genuine uncertainty embedded in nearly every term of that equation is exactly the space in which the Fermi paradox and the various attempts to resolve it actually live. But in 1996, and in a more detailed follow-up paper published in 1998, an economist and polymath named Robin Hanson, then at George Mason University, proposed something structurally different from all of these. Rather than picking a single explanation, Hanson reframed the entire question. He argued that the path from lifeless chemistry to a galaxy-spanning, technologically advanced civilization isn't a single leap. It's a long chain of separate sequential steps, and he laid out roughly 9 of them: the emergence of a reproducible molecule like RNA, the development of simple single-celled life, the jump to complex cells, the emergence of sexual reproduction, the rise of multicellular organisms, the evolution of genuine intelligence, the development of tool use and technology, and finally, the transition into an expansionist interstellar civilization capable of colonizing other star systems. Hanson's core insight was this: somewhere along that entire chain, from dead matter all the way to galaxy-spanning civilization, there must exist at least one step so staggeringly improbable, so difficult to actually achieve, that it filters out almost every single planet, every single budding form of life that ever attempts to pass through it. He called this obstacle the Great Filter, and its existence isn't really optional or up for debate. Given how empty and silent the observable universe genuinely appears to be, despite the sheer number of planets that should, statistically, have already produced spacefaring civilizations, some kind of filter has to exist somewhere along that chain. The real, open, and deeply consequential question isn't whether the filter is real, it's where exactly it sits. This is where Hanson's theory stops being a tidy academic abstraction and starts becoming something considerably more personal, because the location of that filter carries dramatically different implications depending on where, in humanity's own history, it turns out to actually sit. If the Great Filter sits behind us, somewhere in our deep evolutionary past, that would actually be good news, relatively speaking. It would mean humanity has already cleared the hardest, rarest, most improbable step in the entire sequence, whatever that step turns out to have been. Perhaps the initial spark of self-replicating molecular life itself, an event that, as far as anyone can tell, only happened once on Earth, roughly 4 billion years ago, and has never been observed occurring anywhere else. Perhaps it was the jump from simple single-celled life to genuinely complex multicellular organisms, a transition that took Earth roughly 2 billion years to achieve after life first appeared. An extraordinarily long, uncertain stretch of time during which nothing more complex than bacteria and simple microbes existed anywhere on the planet. There's genuine, hard-won scientific evidence supporting the idea that at least some of these early steps really were extraordinarily improbable. The jump from simple bacterial cells to the more complex cell structure found in every plant, animal, and fungus on Earth, a transition biologists call the emergence of eukaryotic life, appears, based on the fossil and genetic record, to have happened only a single time in Earth's entire 4 billion year history, an event so singular and so difficult to replicate that some biologists have specifically flagged it as one of the strongest individual candidates for where a genuine filter might sit. If a transition that consequential really did only happen once, by pure chance, in the entire history of a planet as biologically productive as Earth, that's a genuinely strong argument that something in our deep past may represent exactly the kind of astronomically improbable barrier Hanson's theory describes. If either of these represents the true filter, then humanity's continued existence and eventual expansion into space would be, relatively speaking, the easy part. We'd have already beaten the odds. The silence of the universe would simply reflect the fact that almost no other planet anywhere ever managed that same improbable first leap. The considerably more unsettling possibility is that the Great Filter sits ahead of us, somewhere in humanity's future, a barrier we haven't yet reached, let alone crossed. Under that scenario, the universe's silence isn't reassuring at all. It's a warning. It would mean that life and even intelligence might actually be common throughout the galaxy, that plenty of civilizations have followed roughly the same path humanity has followed, reaching roughly the same technological milestones we've reached today, and then, almost without exception, something stops them. Something prevents virtually every single one of those civilizations from ever making the leap into a long-lived, visible, spacefaring presence. something so consistently, universally lethal, that it has apparently silenced every single other example across the entire observable universe without leaving behind a single confirmed trace. As Hansen himself put it in his original writing on the subject, that scenario carries genuinely dark implications for humanity's own long-term prospects. If a filter this severe still lies ahead of us, then Earth's civilization, however advanced and confident it currently feels, may simply be next in line. If the filter really does lie ahead of humanity, the natural immediate question becomes, what specifically could possibly be lethal and consistent enough to silence essentially every single technological civilization that has ever emerged anywhere in the galaxy, without exception? Researchers who take this scenario seriously have proposed several genuinely plausible categories of threat, and it's worth being clear that none of these require anything exotic or supernatural. Nuclear or biological self-destruction sits near the top of most lists. The straightforward possibility that any civilization advanced enough to develop interstellar travel is, almost by definition, also advanced enough to develop weapons capable of destroying itself entirely, and that the historical window between capable of building rockets and capable of building weapons that end civilization may simply be too narrow and too dangerous for most civilizations to successfully navigate. Given that humanity itself first split the atom and reached space within the same 70-year stretch of the 20th century, this isn't an abstract hypothetical. It's a genuine documented feature of our own recent history. Environmental or ecological collapse represents another serious candidate. The possibility that any sufficiently advanced technological civilization inevitably, and perhaps unavoidably, degrades the very planetary systems that sustain it, whether through resource exhaustion, catastrophic climate disruption, or some other form of self-inflicted ecological unraveling, before that civilization ever manages to establish a genuinely independent, self-sustaining presence beyond its homeworld. Uncontrolled or poorly aligned artificial intelligence has become an increasingly discussed candidate in recent years as well. The possibility that any civilization advancing rapidly enough to approach interstellar capability will, along the way, also develop machine intelligence significantly more capable than its own creators, without necessarily developing the wisdom, foresight, or control mechanisms needed to ensure that intelligence remains safely aligned with its creator's own survival and interests. There are less anthropocentric possibilities, too. Threats that wouldn't have anything to do with a civilization's own choices or mistakes at all. Catastrophic natural events like large asteroid impacts, nearby supernova explosions, or gamma-ray bursts capable of sterilizing a planet's surface with essentially no warning and no possible defense, regardless of how technologically sophisticated the civilization living there happens to be. None of these proposed filters requires anything resembling malicious aliens, ancient curses, or hidden conspiracies. Every single one of them is a serious, grounded, entirely plausible extension of dynamics we can already observe directly in humanity's own relatively brief technological history. That's precisely what makes the Great Filter genuinely different from typical science fiction speculation about alien life. It isn't really a theory about aliens at all. It's fundamentally a theory about us, using the profound, otherwise unexplained silence of the entire observable universe as indirect statistical evidence about the odds our own civilization is currently facing. There's a second related idea that has gained enormous traction in recent years, one that offers a genuinely different and in some ways even more unsettling explanation for the universe's silence, one that doesn't require civilizations to be destroying themselves at all. The idea is called the dark forest hypothesis, and it was popularized by Chinese science fiction author Liu Cixin in his acclaimed novel The Three-Body Problem, though its core logic draws on genuine game theory and evolutionary reasoning that extends well beyond the pages of fiction. The hypothesis proposes a chillingly simple picture of the universe. Imagine the galaxy as an enormous, pitch-dark forest, and every civilization within it as a silent, armed hunter moving carefully through the trees. Every hunter in that forest desperately wants to survive. Every hunter understands that other hunters exist somewhere out there, hidden among the trees. And critically, no hunter can ever be entirely certain whether an unfamiliar sound coming from the darkness belongs to a fellow hunter who might be friendly or a genuine predator who might not be. Under those specific conditions, game theory suggests a brutally rational strategy naturally emerges. Stay silent, and if you ever do detect another hunter's presence, eliminate the potential threat immediately and from as safe a distance as possible, before they ever get the chance to do the same to you. Broadcasting your own location, deliberately or not, becomes an act of enormous, potentially fatal risk, because there is no reliable way to distinguish, from a distance and across a communication gap that could easily span centuries, whether the civilization you're signaling to is friendly, indifferent, or genuinely existentially dangerous. Applied to the actual universe, The dark forest hypothesis suggests that the silence we observe isn't necessarily evidence that nobody else is out there. It may instead be evidence that everybody out there has independently, rationally, arrived at exactly the same terrifying conclusion. The safest possible strategy in a universe where you cannot verify anyone else's intentions is to say absolutely nothing at all, and to treat any confirmed detection of another civilization as an immediate existential threat requiring a decisive response. This idea carries genuine, direct relevance to real, ongoing scientific debate, not just as a piece of speculative fiction. It sits at the heart of a serious, long-running disagreement within the scientific community over so-called active SETI, or messaging extraterrestrial intelligence, the practice of deliberately transmitting powerful targeted signals out into the galaxy in hopes of provoking a response rather than simply passively listening for one. Prominent physicists, including the late Stephen Hawking, publicly warned against this practice, arguing that deliberately announcing our presence and location to an unknown universe without any way of assessing who or what might be listening could carry genuinely catastrophic risk. Others argue the concern is overstated, pointing out that Earth has already been leaking radio and television signals out into space for the better part of a century regardless of any deliberate messaging effort, meaning any civilization advanced enough to pose a genuine threat has very likely already had ample opportunity to detect us anyway. It's worth pausing here to address something directly, because it's genuinely part of why this particular theory carries the reputation it does. Serious scientists don't typically avoid discussing the Great Filter because they think it's fringe, unscientific, or embarrassing. They approach it carefully because of exactly how consequential and how genuinely unresolved its implications actually are. Unlike most scientific theories, the Great Filter doesn't come with an obvious, testable path toward direct confirmation. We can't currently send a probe out to survey the galaxy and empirically count how many civilizations successfully passed each of Hansen's 9 proposed steps, and how many failed at each stage. What we're left with instead is an extended, uncomfortable exercise in probabilistic reasoning, drawing broad, sobering inferences from a single, stark, undeniable data point: total silence, across 60 years of dedicated searching, across an observable universe containing an almost incomprehensibly large number of stars and planets. That's an inherently difficult, methodologically humbling kind of science to conduct with real rigor, and reputable researchers are appropriately cautious about overstating conclusions built on a foundation this thin. There's also a genuine, understandable reluctance among many scientists to be seen publicly speculating about existential risk to human civilization in a way that might come across as sensationalist, alarmist, or worse, indistinguishable from the kind of unfounded doomsday content that circulates constantly online. Robin Hansen himself has been remarkably candid about this exact tension in his own public writing and interviews, repeatedly emphasizing that the Great Filter is best understood not as a specific, confirmed prediction of impending catastrophe, but as a genuine, serious, probabilistic framework, a tool for organized thinking about deeply uncertain terrain, rather than a definitive verdict on humanity's fate. That careful hedged framing doesn't make the underlying question any less serious. If anything, it's precisely the kind of honest epistemic humility that responsible science demands when grappling with a question this genuinely consequential, and this genuinely difficult to test. And yet, despite that caution, an increasing number of serious, credentialed voices have been willing to engage with the Great Filter directly and publicly in recent years. Philosopher Nick Bostrom, director of the Future of Humanity Institute at Oxford, wrote in a widely circulated 2008 essay that discovering any evidence of even simple microbial life on Mars would, counterintuitively, actually be troubling news for humanity's own prospects, precisely because it would suggest that the emergence of basic life itself isn't a particularly rare or improbable step, which would push the location of the Great Filter later along the chain, closer to our own present moment and closer to our own future, rather than safely behind us in the deep evolutionary past. That's a genuinely striking, counterintuitive claim that finding alien life could actually be bad news rather than good news. And it's exactly the kind of carefully reasoned, uncomfortable conclusion that makes the entire Great Filter framework so difficult to dismiss as mere speculation. Here's where all of this theoretical framework connects back to something genuinely, concretely measurable: the actual, real, ongoing search for extraterrestrial intelligence, and its equally real, ongoing lack of results. The search for extraterrestrial intelligence, known as SETI, has been conducting organized, systematic radio searches for potential alien signals since 1960, when astronomer Frank Drake pointed a radio telescope at 2 nearby Sun-like stars in what became known as Project Ozma, the first dedicated scientific search of its kind. In the 60-plus years since, that search has expanded dramatically in scope and sensitivity, from small individual telescope campaigns to massive, coordinated modern efforts like the Breakthrough Listen initiative, Launched in 2015 with tens of millions of dollars in dedicated funding, using some of the most powerful radio telescopes on Earth to systematically scan 1 million of the nearest stars and the entirety of the galactic plane for any sign of an artificial signal. The result, across all of that accumulated effort, remains unchanged. Nothing. No confirmed signal, no repeating, unambiguous artificial transmission that has ever survived rigorous scientific scrutiny. This isn't in itself definitive proof that nobody else is out there. 60 years of searching, however extensive, still represents an almost vanishingly small fraction of the total sky, the total range of possible frequencies, and the total span of cosmic time across which a signal might theoretically have been sent and subsequently missed entirely. But that accumulated silence does carry genuine, if inherently probabilistic, statistical weight. Each additional year, each additional star system checked, each additional survey completed without a single confirmed detection, incrementally strengthens the case that something is preventing the kind of loud, detectable galaxy-filling civilization the raw numbers originally suggested we should already be observing. That's precisely the epistemic tightrope the Great Filter asks us to walk. It doesn't claim we found conclusive proof of exactly where the filter sits, or exactly what form it will ultimately take. What it does, honestly and rigorously, is take an otherwise genuinely mysterious cosmic silence and turn it into a structured, serious framework for asking exactly the right question, the one Fermi first stumbled onto over lunch in 1950, and the one that has never actually gone away in the 75 years since. Given how empty and silent the universe genuinely appears to be, what does that emptiness actually suggest about the odds facing any civilization, including our own, currently standing at roughly the same technological threshold we occupy today? Step back. And here's the honest shape of the whole story. The Great Filter isn't a theory about alien monsters lurking in the dark, waiting to destroy us. It isn't a claim that scientists have discovered some hidden, terrifying truth they're deliberately concealing from the public. It's something considerably more sobering and considerably more grounded in legitimate, careful reasoning, a serious, structured framework built by an actual working economist and refined by decades of subsequent scientific and philosophical debate for taking one of the most striking, well-documented observations in the entire history of astronomy, the complete and total silence of an unimaginably vast universe, and asking exactly what that silence should rationally lead us to conclude about our own civilization's prospects. If the filter sits behind us, in whatever improbable spark first turned dead chemistry into living, replicating molecules 4 billion years ago, then humanity has already beaten odds so long that a truly empty universe is exactly what we should expect to see, and our own long-term future, while never guaranteed, at least isn't laboring under some universal, inescapable curse. If the filter sits ahead of us, in some combination of self-inflicted catastrophe, environmental collapse, uncontrolled artificial intelligence, or some other threat we haven't yet fully identified or reckoned with, then the silence carries a very different message entirely. A statistical warning drawn from the fate of every other civilization that may have once stood exactly where humanity stands today, and simply never made it any further. Nobody currently knows with any real certainty which of those two possibilities is actually true. That uncertainty is precisely the point, and precisely why serious researchers engage with this question so carefully, rather than dismissing it outright or sensationalizing it into easy, comfortable answers. The Great Filter doesn't hand us a verdict. It hands us a mirror, pointed directly at our own species, at the exact moment in our history when we finally developed the tools capable of asking the question seriously, and just possibly, if we're being honest and careful enough about the answer, the tools capable of doing something about it. If this changed how you think about the silence in the night sky, let me know in the comments whether you think humanity's own Great Filter is more likely sitting behind us or still somewhere ahead. And if you want to keep exploring the biggest, most genuinely unresolved questions at the edge of real science, subscribe, because the silence out there isn't going anywhere, and neither is the question of exactly what it means.